In this video, I will explain you Einstein's equation of photoelectric current. Now, we have learned that light or radiation having sufficient energy when incident on metallic surface, this will be able to take electron out of metallic surface. These electrons are termed as photoelectron, and this phenomenon is called as photoelectric emission. Now, we know that the radiation having a frequency of mu will be associated with an energy of h nu. So what is the total energy that the radiation carries? That is h into nu, which is frequency of that incoming radiation. So total energy carried by radiation. This is the value of energy h nu, and this much amount of energy is now given to electron, right? Electrons are in the outermost orbit of an atom. So total energy imparted to electron, it will be the same amount of energy conservation. What will happen? Radiations are coming. Now this energy is being transferred to an electron in the orbit, or maybe a free electron, any of this. So we will consider it as electron in the orbit. So the total energy is now imparted to electron is the same energy, h nu. Now out of this much energy, a part will be used as work function. What is work function? To take an electron out of the metal surface. So energy consumed as work function. How much is that? Work function. We have learned the value is equal to 5, which is equal to h into mu 0. What is mu 0? Threshold frequency. Okay. Now, if this much amount is consumed, then what is remaining? That is h nu minus h nu 0 is remaining. Where will this energy go? That energy will be the kinetic energy of the moving electron. So radiation comes, and out of that, so h nu is coming, out of that phi is taken for the photoelectric emission. Now this emitted electron will be here. So with just phi, it can only come out of the metallic surface and have zero velocity. Now if h nu is more than phi, the additional energy will be given as the kinetic energy of moving electron. So that will be half mv square. Now h nu minus phi, if it is higher, what is that? See, out of h nu, phi will be used as work function, and the remaining will be given as kinetic energy. Now higher the remaining amount, higher the remainder, higher will be the velocity of moving electron. So mass of the electron is fixed, only the velocity can change, so thereby it will adjust its kinetic energy. So now kinetic energy of electron is equal to, from incoming radiation h nu, work function is consumed, and this is equal to the kinetic energy. And I have one more equation, h nu minus work function, we know that it is h nu 0, where nu 0 is the threshold frequency. So this value is equal to h into mu minus mu 0. Either this equation h nu minus work function or h into frequency of the radiation minus threshold frequency. Now, so this will be having an energy in this way. So with that energy, it will be moving towards the positive plate. This is collector plate. Now, if I am giving a negative potential here, so instead of this, if I am giving negative potential, which means negative side of the battery I am connecting with this, and positive I am connecting here. Now this will be giving the negative potential, will be giving negative plate, will be giving a potential, negative potential here, which is minus V. Okay, now as there is a charge of E here, the total potential energy here will be E into V, because we know that potential energy is equal to QV. So here it is negative potential and charge is QE, so the value will be minus EV. Now this is the potential energy, and we have kinetic energy in this way. What is that value? half mv square. Now if it is having energy, then only it can move, right? If the net energy is 0, it can't move. So let's assume that this value of the potential is such value that the EV become half mv square. I will repeat again. What will be the total energy here? Total energy at this position is equal to half mv square is the kinetic energy of the electron here, and due to the negative potential here, this will have a potential energy of EV. Now if these two value is equal, this will be having a zero velocity, which means photoelectric emission is not possible. See, no energy means electron will not reach here, there won't be current passing through this circuit. Okay, now this is the kinetic energy, right? So we have learned from the previous example that when the potential at this point becomes stopping potential V0, then there won't be current passing through the circuit. That is what we have learned. With intensity we have learned curve like this, curve like this. This was the potential, stopping potential I1, I2, I3. Now with different frequency we have learned that lower the frequency, lower is the stopping potential. Higher the frequency, higher is the stopping potential. See, this is mu1, mu2, mu3, where mu3 is greater than mu2 is greater than mu1, and we have learned that energy, kinetic energy of the emitted electron is a function of the frequency. Higher the frequency, higher will be the kinetic energy. To stop that kinetic energy, we need higher stopping potential. So it have to be shifted here with a small increment in frequency, then again have to be shifted if you are again increasing the frequency. Now this kinetic energy, if that becomes, if we are giving a potential of stopping potential, that both will become equal and photoelectric emission is not possible. So at that point I can say that E into V0, the stopping potential, when it becomes the kinetic energy, the total energy is 0, I could say that emission will not be possible. So at that case, I can equate kinetic energy is equal to this. All other cases, there will be a non-zero value of kinetic energy. Now if I am giving a small potential here, if that is not equal to the kinetic energy, now this is small, it can come here. But when this is equal to this one, it has no energy, it cannot come. So only at that position where the kinetic energy will be equal to this one, when the potential applied is stopping potential, these two will be equal, and I can equate with this H into mu minus mu 0 or H nu minus work function. So these equations can be used according to the question. Either this equation you can use E into stopping potential is equal to H into frequency of rate. This is the frequency of incoming radiation, this is the threshold frequency. If threshold frequency is not given, instead of that, if work function is given, H nu is the energy of the incoming radiation, work function, phi is the work function, that is part of incoming radiation consumed to, consumed for an electron to come out of the surface. So according to the question, you can use different values. Now use this equation KE max. This is the maximum kinetic energy, right? KE max is equal to H nu minus phi. Why do I call it as maximum kinetic energy? Because from the incoming radiation, just phi is used. Everything remaining has become kinetic energy. With some electron, see what will happen now? Out of 100 joule, let's say 10 joule is the work function, it is consumed, now remaining is 90 joule. Now this 90 joule can become kinetic energy. See, 100 joule is the radiation and 10 joule is the work function, remaining is 90 joule, and that can fully convert as kinetic energy. But in some cases a part of it will be used here to move the electron from this position till this position. Maybe 30 joule will be used. Now for the coming electron, maybe remaining is possible. What is that? From 90, 60 will be possible. So maximum kinetic energy is always will be obtained with the subtraction of work function from the energy of incoming radiation. This is very, very important. Okay, and the kinetic energy is always a function of incoming radiation. Now see, for a material, its work function will not change. Now with the same material, if you are changing the frequency of incoming radiation, now the frequency is 100. Now if you are changing into 150, this value will change. Now this will remain the same. For example, you have a copper rod, so copper will be having same work function. Now you are using different color. With red, frequency is different. With blue, frequency is different. With violet, frequency is different. So when you are increasing the frequency, the total value of HNU will increase, keeping phi same, so that this value will keep on increase. Why? This is getting increased. Now when this value getting increased, kinetic energy of maximum kinetic energy of electron will also increase. Now to stop that, we have to apply higher stopping potential. That is happening here. Lower frequency, lower potential, stopping potential, we can stop it. Higher the frequency, kinetic energy of emitted electron will be more. Now we need higher stopping potential. Highest the frequency, highest will be the maximum kinetic energy of emitted electron. So we need higher stopping potential to stop the emitted electron. Okay, thank you.